lecture series. If you've been joining us for all of our events, the Friends of Lick Folo Family Dinner, our Ask an Astronomer, and of course, these living room lectures, you've had a lot of fun with us as we have explored everything from supernova to black holes, to our observatories and the instrumentation that we use to make our science possible. This week, we have a special treat for you. We get to hear directly from Dr. Shelley Wright, who will be talking to us about the search for extraterrestrial intelligence. Dr. Wright is an associate professor of physics at UC San Diego in the Center for Astrophysics and Space Sciences. As many of you know, her research focuses on developing innovative astronomical instrumentation and observations using some of the world's largest optical telescopes. She specializes in near-infrared cameras and spectrographs and studying distant galaxies and supermassive black holes. She's also been involved with the search for extraterrestrial intelligence. Those of you here in Silicon Valley know them as SETI. The instrumentation on UCO instruments, including working on a FirstLight instrument, IRIS, for the 30-meter telescope, as well as new instrumentation for Keck Observatory. Joining us from her living room or wherever she was able to find a quiet space this afternoon, Dr. Shelley Wright, thank you so much.
Hello, everybody. I hope everybody's well during these incredibly challenging times for our globe. I'm calling from my house. I have two little ones, so I cannot promise that you will not hear them, and I hope they don't burst in, but they just might. So I appreciate sharing my home to you and for all of you to join today. I'm going to talk about one of my favorite topics, and in fact, what got me into astrophysics in the first place as a little girl. And I'm going to tell you a little bit about my story through this process and how I came to be a professor and interested in SETI. So this is a little bit of an arc to it. I think it's a great topic. We're going to have a lot of fun. Please, if you have questions, just write them in the chat stream as we go. And I'm going to try to leave time at the end so we can answer some of these questions. So to get started, let me share my screen. Share. Okay, so part of this story has to do with Lick Observatory. And as I will describe, I'll be talking about SETI, which is the search for extraterrestrial intelligence. And some of the story I'll be telling happens to be in that building. If you've been to the main building at Lick Observatory, you may have even seen old pictures of instrumentation that involves SETI there. And I'll talk about some of the latest SETI instruments that were just installed in 2020 that's sitting in my background screen here. So I'll get this. These pictures were taken by Lori Hatch. If you know her work at UCO, and in particular Lick and Keck Observatory, just a call out to her and her wonderful photography. Okay, so here we are. We're all sitting at our house. So I want to kind of start in a big picture sense here. Here's my blank screen. I have a blank screen here on purpose because I want all of us to think about, it sounds funny to say, but I want everyone to close their eyes and think about waking up tomorrow morning. And the first thing they look at the news, can you imagine, given everything that is in the news, is that scientists have unambiguously detected a signal from extraterrestrial intelligence. And I want you to think about, in that moment, reading this, and all of the thoughts and feelings that would swell up in that moment for you. You're on this call, you probably thought about this question, you probably thought about this answer. And its impact to humanity and its impact to science. So this is a big picture question, right, that we're trying to strive to answer. And I'll return to some of this at the end, but I wanted each and one of us to think about this. And especially think about it in the context of how we do the pursuit to answer this question in science. Okay, all right. This is great that it's actually in the living room because we can have our wine and think about these topics. It's kind of a good glass of wine topic or beer. Okay, so here we go. I'm going to show you my most favorite picture that's ever been taken by humans. This is it. Okay, this is a piece of it. It's the Hubble Ultra Deep Field. Okay, and it was taken by the Hubble spacecraft. If you hold out your arm, let's see if this works in my screen, and you had a pencil tip at the tip of it, the area at that tip is the area of this picture. And the Hubble Space Telescope opened its shutters for 50 plus days to allow the light from distant galaxies that are tens of billions of light years away to come in to make this image. So everything you see here is another galaxy, except for this little foreground star that's within our own Milky Way. I love this image because it gives us one of the best cosmic context and the breadth of the universe and how large it is. So every little smudge, even this little tiny smudge, if you can see it on your screen here, is another galaxy. Okay, so what are galaxies, right? Galaxies are structures that contain hundreds and billions of stars. So this is a nearby galaxy like our own. In fact, it's the same type of Hubble type as we like to call for galaxies. It has a beautiful core here with a bulge, gorgeous spiral arms with newly formed stars forming in it. It's a face-on galaxy, so if we flew out of the Milky Way, this is what we would look like. And our star, right, is one of hundreds of billions of stars in our Milky Way. Okay? And in that Hubble deep field, if you take the observable universe, we know that there's hundreds of billions of galaxies. So here's our math. We're going to do some math today. Hundreds of billions of galaxies multiplied by hundreds of billions of stars. What does it equal? I love thinking about high order magnitude, big things. My answer is always a whole lot of stars. Like no matter what, that is a bunch of stars. Okay, and our home of planet Earth is around just one of 10 to the 22 stars in the universe. So when we think about the context of other life in the universe, right, it's important to think of large numbers, which we like to think about in astronomy. Of course, we'll think about time, right, and think about lifetimes for us here. But that's just a little context of where we are. All right. Okay, so thinking about SETI is nothing that's not new. Philosophers have been doing this for centuries and thousands of years. I like this quote. This was taken from the Tungmu Sung dynasty in 1000 AD. It says, empty space is like a kingdom, and earth and sky are no more than a single individual person in that kingdom. Upon one tree are many fruits, and in one kingdom there are many people. How unreasonable it would be to suppose that besides the earth and sky we can see, there are no other skies and no other earths. So speculating about this, and even what drew us to this Zoom call today, has been with us for eons. So in that context, if we know that there's hundreds of billions and 10 to the 22 stars out there, we need to ask the question of how many planets there are around other stars. And thankfully, astronomers have been able to answer this question in the last 15 years through missions like the Kepler Space Telescope and some of the initial research done at Lick Observatory looking for extrasolar planets. And the answer that we have, at least within the solar neighborhood around our own sun, is that about 1 out of 5 stars has an Earth-sized planet. Not Earth-like, but Earth-sized, okay? So if you like to count and go out to star watching, which I'm sure many of you do, I like to count in fives, 1, 2, 3, 4, 5. Oh my goodness, that has another Earth-sized planet on it. Okay. And it turns out that the most common type of planet are what are called super Earths. There's a debate within the exoplanet community, and they're sometimes called mini Neptunes, okay? And interestingly enough, our solar system doesn't even have one of these. And the more we learn about extrasolar planets, we learn that they're quite diverse. They come in all different shapes and sizes. This has given us astronomers many things to speculate about and explore about the fundamental understanding of how solar systems even form. And it's even bringing us into this next decade to ask the question of what are the atmospheres like on these other worlds? Do they have liquid water? Do they have even biosignatures from other life forms? And so astronomers and astrobiologists in this next decade are going to try to answer this with some of the largest facilities. Now, for today's talk, we're going to kind of take a big leap here and ask a question not just about life, but about whether there's other civilizations out there and whether those civilizations would be communicating right now. And try to calculate this was first proposed by Frank Drake, okay? And he came up with the Drake equation, which tried to find out how many civilizations exist with us today. Okay, we're one in the Milky Way. Are there others? And to answer this question, you need to know a number of factors. So here's our other set of math for today that I like to do. I'm gonna go through my own spin of the Drake equation, and I welcome all of you at home, if you have a piece of paper, goodness, bring it out. Let's do the Drake equation together. Okay, so we're gonna try to calculate the number of civilizations right now in the Milky Way. Okay. So we have several factors for this. So n civ is the number of civilizations, equals to the number of stars, okay, multiplied by the fraction of habitable planets, multiplied by the fraction of those planets where life exists, and multiplied by the fraction of those where civilizations exist, and then multiplied by that fraction now. The time matters. So let's go through this. I'm going to go through my own calculation. Let's say there's 200 billion stars in this calculation. Yeah, there's lots of papers that go back and forth on the number of stars in Milky Way. We're going to do 200 billion today. Fraction of habitable planets, okay, 1% to 10%. Okay. Fraction of life that exist, 10% to 100%. Okay. Fractions of civilizations, let's say it's 1%, right? And you may think these numbers are wildly optimistic. That's fine. Now, let's look at the fraction now. What if we say civilizations live for 10 million years? Okay. And I'm sure many of you right now in COVID world are thinking, oh goodness, is that even possible? So let's take that fraction that we can survive for 10 million years here. Then the answer to this is that the number of civilizations is 1 in 100 million to 1 in a million. Then there would be 2,000 or 200,000 civilizations today in the Milky Way. But I love this. If you're an archaeologist, think about this, guys, then there would have been 2 to 200 million before. And so a key thing in this calculation comes out, and this was caught early on by Frank Drake. It was caught early on and spoken a lot about by Carl Sagan in many of his books, which is the lifetime of the civilization. If all these factors in the Drake equation matter the most, okay, if you want to think about whether we exist with others today. All right, so I do this in class, and you know, I have a lot of people shake their heads about this, 10 million years. So let's look at it a little differently. Maybe this isn't the way to go here, but let's say civilizations live for 10,000 years. That's 1 in 100 billion to 1 in a billion. So if civilizations only last 10,000 years, then there are only 2 to 200 that exist today in the Milky Way with us. Okay. And I hope this shows the issue of time, right? And the sliver of time that we're occupying with our technology, and the sliver of time that if there was another existing communicating civilization that would have to coexist during that exact time. Okay. Hopefully, if you guys had fun with this, there's many versions. There's even online calculators. You can go on and play with the Drake equation. Okay, so if there was another extraterrestrial intelligent civilization existing with us right now, what methods of communication do you think that they would be using to send us a message here on Earth? How would we detect something if somebody was coexisting with us? So how do we do that? So how do we communicate over long distance today? And one of the key themes you'll see in my talk is that we're obviously limited to what our technology is, right, today in 2020. So how do we do it? Well, we do mail, okay? So I could write you a letter and we postmark it, it gets sent. Okay? In fact, there's been papers in SETI where people say, oh, the best method is actually just kind of writing a note and kind of throwing a rock out there. And in fact, that's, if you think about our satellites, that's exactly what we're doing. We've also draped planet Earth in previous times and still do in telephone lines. But our most common method for long distance communication is radio. Okay? And we learned that many decades ago to do long range communication, not just here on planet Earth within our atmosphere, but also to satellites and other places within our solar system. And then all of us amazingly have this wonderful little tiny computer in our handheld computer in our cell phone And that's done with cell phone lines and towers and satellites. So there's a common theme here, which is that how we communicate is through the electromagnetic spectrum. And so in SETI, this is how scientific method and the scientific process has looked at this thus far. Okay. So we use light as our carrier. It's great. Light's the fastest you can go, so it's going to get there as quick as possible. Okay. You can pack a lot of information into light, but you need to select a frequency. So you can do radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, low frequency to high frequency. There's a advantage to each of those potentially, right? Low frequency, we have lower energies to generate it. Okay? And it was at this reason which we first started looking at SETI for scientific reasons for our carriers. Now, the first published SETI paper in human history was by Kokone and Morrison in 1959. And they have a wonderful famous quote in it, which is, "The probability of success is difficult to estimate, but if we never search, the chance of success is 0. And the phase space for SETI, it is huge. We have many things to consider when we look at it. And I just gave you one big one, which is if you think that the message is being communicated via light, what frequency of light would it be communicated with? Now, one of the first SETI searches that was kind of a mishap here was Nikola Tesla was very interested in looking about how to do communication, not communication, but also how to do electricity, right, without wires. And he would build large experiments like Tesla coils to do this. He built one of these in Colorado Boulder, and Nikola Tesla was obsessed that there were Martians. And he once got a signal with his experiment in Boulder and immediately went to the presses and to the scientific community and said that he had detected Martians. Okay, and you see one of this, how the scientists and the public responded. They said, "To Mars with Tesla." Okay. And I always put this because this is one of the first lessons in SETI, is that we have to be darn sure that the signal we receive is real, okay? And we have to worry about what's called false positives, okay? We need to make sure that the signal's ambiguous. Okay. Also, years after, David Todd was an astronomer, and he too was convinced that there were Martians. Okay. And he did something interesting, which is he requested a day of radio silence. Okay, so this is a telegram he sent, a military cable, where he requested that we allow all the radio silence from our Navy bases and allow us to search for radio signals from Mars. So these are kind of the first couple. You can kind of see SETI searches, but they're not thinking too far. They're just thinking that our nearby neighbors are within our own solar system. What we consider to be the real first SETI search outside of our solar system was Project Ozma in 1960. And as you can see, we have a 60th anniversary to this event. Okay, we were actually, there was many of us supposed to go to Green Bank Telescope, which was here, but it got canceled due to COVID. Frank Drake had his 90th birthday also this year to celebrate him and his first endeavor here. He used this large disk, the Green Bank Telescope, and looked at 2 stars, Tau Ceti and Epsilon Eridani, and he looked at specific frequencies at radio to see if there was any communication. And this really was the birth of the SETI endeavor. So that launched a number of things within different SETI programs, and that was pushed for a while then, but eventually those efforts got cut. And I do a shout out to this book and movie, which I think stands the test of time. Contact was a book written by Carl Sagan. If I was with you all, I'd ask you all raise your hand to see how many of you've read it. I bet this is a selection effect of who's on the call. If you haven't seen the movie, I really recommend it. The first third of the movie is really a true story. Okay? And it's about Jill Tarter, who is played by Jodie Foster, and looking at using radio frequencies for a signal. The last 2/3 where Carl really got creative was obviously what would happen next if there was communication. So while we got cut from funding from Congress, which I'll talk a little bit about later, we've been struggling with this. So SETI has not been publicly funded for many, many decades. And most of the SETI experiments I'll describe to you has been done through philanthropic means. Many of us are trying to change this now. Okay, so, sorry, just 1 second. Let me move that, okay. So Project Phoenix, which was also, Arecibo is in this, at the film. I think it starts with Jodie Foster there if you've seen it. Jill Tarter started a program there to look at 710 stars, all within 150 light years, because one of the ideas was if there was to be a signal sent to us, they would have to be nearby neighbors and know potentially that we're here. And Jill's strategy was to basically look at a small number of stars, but look at many frequencies at once. So they looked at 70 million radio channels, okay, to see if there was any signals coming from these stars. It's the most sensitive radio search ever performed up into about this year. In fact, there's another instrument called MERCAT that's just coming online that's just as sensitive, which is amazing because this Wright was in the 80s and the 90s. But I want to point out one thing. This is what we call a targeted search, meaning we are looking at individual stars. So think of little soda straws on the beam of the sky, okay, but at many channels. Similarly, there is also a group at Berkeley that did piggyback observations. So Arecibo's fixed, the Earth is rotating. It would look at many different signals across the sky, and they would pick off several of those frequencies to look for SETI signals. Okay? And so this was kind of what we call a wide field search, but it was shallower because they could only pick out some of the light and some of the frequencies. But what came out of this program, which was called Serendip, was SETI at home. And Dan Werntheimer and others at Berkeley developed a background screensaver that would allow a user to download the data and crunch the data on its own computer. And this started distributed computing. Okay, so I love this example because sometimes when we think about how to do SETI searches, we can kind of open up a new realm here. Today, there's about 8.4 million users and 226 countries involved with SETI at home. And they would download the data from Serendip, crunch it over time. I remember my first computer or my second computer did this, and I was super excited about it. This was even before I was just doing my studies as an undergrad. Okay. So this is SETI at home, and it later evolved to many different platforms that Berkeley's now involved with. Okay. So similar for radio, there's the Allen Telescope Array. The SETI Institute started this program. The idea was to build a large array of 350 telescopes, each 6 meters in diameter. This was to be located up near Mount Lassen in the north. It was to look at large frequency ranges from 0.5 to 11 gigahertz if you're into the radio frequencies. But in 2008, it ran into a huge funding crisis when we had the 2008 crash. And so today there's only 42 arrays installed. But as of this year, there are actually new receivers and new work being done by Berkeley and the SETI Institute to revitalize this program. Uh-oh, someone's coloring. That's not me. Okay, so I just gave you kind of a potpourri, I would say, of some radio searches. One thing I want to point out to this is that SETI searches scale directly with Moore's law, right? We do as well as we can do with the technology and our available resources we have today. So this is looking at the number of simultaneous frequencies versus time. Okay, the line is Moore's law, and this is on the dots here represent the things we just talked about, like Serendip. Here's Project Phoenix. Okay, here's Project Ozma all the way back in 1960. So I get this question a lot, which is, we've looked for over 50 years. Should we call it a day? It must mean that nobody's out there. And I always go to this cartoon because I think it summarizes it quite well, which is there's two ants, right? And they're hanging out and they're talking on the floor. And one of the ants is like, we've searched dozens of these floor tiles for several common types of pheromone trails. If they were intelligent life up here or here or there, we would have seen its message by now. And the caption is, the world's first ant colony to achieve sentience calls off the search for us, right? So of course, ants don't have their own communication method, right? And what the majority of the way we've communicated or looked for communication from SETI is at radio frequencies. So maybe we just need to think more about different ways to communicate. So the answer is we've barely searched. Here's that Project Phoenix in red that shows the sensitivity. You see how it has very high sensitivity. On this scale is the fraction of the sky. And then here's the frequency, okay, of its search. So Project Phoenix looked at many, many frequencies at radio, got high sensitivity, but it didn't look very far in the plane of the sky. While other things like Meta and Ceridip tried to look at large patches of the sky, but only at a few frequencies. Okay, so you already see the dilemma here. But the answer is we barely searched. And Jill Tarter always relates this as, you know, you take a pint glass and you put it in the ocean, okay, and you look in the ocean and there's no fish. There's no fish. Okay. Thank you. There are no fish in that. There's no fish in the pint glass, therefore there's no fish in the ocean. Okay. And so we've basically looked, if you imagine we want to search the entire ocean, we've only looked at a pint glass of water. Okay. The parameter space is huge. Okay. Some people even say it's so huge we shouldn't even try. But we have many methods out there, and the searches are typically only at radio frequencies. So at the same time that Project Ozma happened, there was Charles Townes, who was in Bell Laboratories making an amazing invention. He was making a laser. So in 1959, Charles Townes invented the laser. And in 1961, only 2 years after his invention, he wrote a paper with Schwartz that basically stated that the laser would be one of the best means for doing interstellar and interplanetary communication. And I'm always completely just humbled by this, that he invented this laser. He knew the industrial applications with it. He predicted it at that time, but he also realized that it was much more far reaching. And in fact, we use lasers today, right, to communicate back and forth between satellites, and are now NASA's doing some of the first missions to communicate to some of the satellites to Mars using lasers. So lasers, if I was with you, I would shine a laser at you guys. Lasers are awesome, they're incredibly bright. They're at single frequencies, but boom, they're incredibly bright. If I shined it to you, would I shine it right here in my camera frame here? It would blind you, right? You have to be careful to look at a laser. So although it's single frequencies, it's very, very bright and it's directive. It doesn't go anywhere else, right? It just goes to the person you want to communicate with. You can modulate that laser. You can pack tons and tons and tons of information into it and send signals within it. And this was recognized early on. But in 1961, we could not do this. We could only use the largest, if we used our largest telescope, which is Palomar, which is close to me in San Diego, which is 200 inches in diameter, we could take the most powerful laser in 1961 and outshine our sun by a factor of 3. Okay, so it could be visible out to about 1/10 of light year, not even close to Alpha Centauri. But if you use today's technology, we can make a 10 to the 15 watt laser. Okay, remember the handheld lasers we hold are in milliwatts. So we can make a 10 to the 15 watt laser, use our largest telescopes in the world, and outshine our sun by a factor of 3,000 across all frequencies, not just by that one wavelength, by all frequencies. It would be visible to thousands of light years away, and you would only need to build a very small receiver to make it. So let me say this again. We have technology in 2020 to essentially send a signal across the entire galaxy and have it received by a telescope that you could handheld. Okay. And if you pause and realize that, you're like, wow, okay, if we can do that, and we're pretty much in our technological infancy, then maybe others could do this or make optical signals as well. So optical SETI, as I said, it's a very bright signal. You only need to look for a bright beacon. So at radio SETI, kind of like you're out in the desert and you're looking for the right radio signals, you'll scan in frequency space. In optical SETI, we're just looking for a big burst of light. Okay, especially if maybe that burst of light is coming from a planet orbiting another star. And so it makes our way of receiving the signal very easy. Hey, over here is what I guess. I hope they send us something more than that, just that, but maybe that would be a good initial letter. Okay, so knowing this, okay, we established in the 1960s, Harvard and Berkeley began some of the first searches in 1998. And they use very fast response detectors, which are called photomultiplier tubes, to make dedicated instruments for this. So this is a picture of Paul Horowitz's group in Harvard. Andrew Howard, who's now a professor at Caltech, was part of this. And this was a dedicated telescope scanning parts of the sky to look for very, very bright bursts of optical signals. So we have our first optical SETI searches. Similarly, this is where I come in. I was fortunate enough when I did my studies at UC Santa Cruz, or as an undergraduate, I worked with Frank Drake there. I worked with Remington Stone and Dan Wertheimer in this image. And we built what's called a targeted search, where we looked at optical frequencies to look for a big, bright pulse of light. And we looked at about 5,000 different stars. And that really is my first entrance into SETI. Now, everything I've described to you right now is up to optical wavelengths. And if you look at the Milky Way, like I have on the screen right now, you'll notice, especially if you even go out at night sky, I hope you guys are out looking at NEO-eyes if it's clear, you'll notice that the Milky Way is patchy. And it's patchy because there's gas and dust within the plane. So I always think we're looking through the Frisbee disk, and this light from the stars is being absorbed by intervening gas and dust. So this is an optical light, visible light for which our eye can see. If you move to longer wavelengths, you get into the infrared. So this is at near infrared wavelengths, just longer than our eye. And this is what the Milky Way would see. Okay, it's transparent. So if you were to send a signal, like a laser signal, you really would want to do this at near infrared or infrared wavelengths. And in fact, all the way back into the 1961 paper, Charles Towns said so. So this was known that the intervening interstellar gas and dust would absorb it. But the problem is we didn't have detectors in the late 90s or in the early 2000s that actually could do this. So when I became a professor, I was very interested in this. Like, how could we take the new cutting edge detectors, near infrared detectors, that are often used for missile range finding and defense purposes, and apply them to astronomy? Okay, and if you like to geek out on this stuff, I love to geek out on it too. I can explain this later and answer questions. But the point is that we worked with companies to develop a near infrared detector that operated similarly to the optical and made the first near infrared SETI instrument. And here's an image of Jerome Mayer. He's a project scientist here with me still at UC San Diego. We were detecting and characterizing these detectors. I didn't say they operate at gigahertz, so they're taking an image every nanosecond. And here's another beautiful image taken by Lori Hatch that shows our internal optics to this. This instrument we put on the Nickel telescope at Lick Observatory. So this has been at Lick since 2015. We've installed it. Here's a picture of our team. And it's, again, a targeted search. So it only looks on a very small patch of sky, and it looks at thousands and thousands of stars. Okay, and undergraduates at UC San Diego have been using this instrument remotely about a dozen nights a month. And we've looked at, I think the number is now over about 3,600 stars, and we have our first papers on it. And no, we didn't detect anything. I wish that was the punchline for today, but no, we did not detect anything. But this was the first move to move into longer frequencies like this for an optical laser search. Okay, so here's the problem. It's a targeted search. I laid out, here's the sun at the center of the image. Here are all the stars we look at within, hundreds of light years. Okay, and we looked at other stars, another interesting phenomenon too with near infrared SETI, but it's little pencil beam surveys. Okay, another way to say this is, here's the plane of the sky, and we look at each one of these dots. Okay, and you look at the dot only for about 10 minutes. And you may ask me, why 10 minutes? And the answer is that, how do I phrase this? The answer we decided on 10 minutes is that if it was longer than 10 minutes, the undergraduates would get bored. So they wanted to be able to learn and move the telescope and move to the next search. And if they was shorter than 10 minutes, it was actually just cumbersome to move to different things. So the answer was a human element of why we look at 10 minutes. We could just look at one patch for years, right? But then you'd only look at one star at a time. And this brings us to a big issue of SETI, which is how do you do a wide field search, okay? And our team was interested in this. How do we make something that can look at the entire sky all of the time? And how do we make a dedicated search for this? So in 2016, we started thinking about this idea, and we have many, many ideas that were thrown into the waste bin until we came up with the idea I'm about to talk about. So we first needed large arrays of detectors. So we need many, many pixels, right? And they had to be fast response detector arrays. So we needed something to operate where we wanted to take nanoseconds. And that's a detail to understand, but it has to do with reading out background signals from either our atmosphere, our detector, and also from a distant source. So we needed to find something that could do that. And it turns out only in the last 3 years, there's actually devices like this hitting the market. The second thing we needed was a way to image the sky, but the entire sky, but in a cost-effective way. And what our team came up with are Fresnel lenses. So this is me. If I was giving my lecture, I would be in my office. I'm not in my office today, but that's my office there in San Diego. And I'm being Fresneled. So I'm sticking a 1/2 meter size Fresnel lens in front of my face, and it's magnifying my face. So this is a 1/2 meter, 20 inches in size. And this little device here, this beautiful imaging lens, is about $300. Okay? The optical properties of Fresnel lenses have gotten so good for mass producing them for projector industries that we wrote several optical papers and tested them. We bought 50 of these lenses around the world from like a dozen companies and tested them and wrote papers about their astronomical use. And so once we had fast detectors that could work in Fresnel lenses, we came up with their design, which is called panoramic SETI. And panoramic SETI, the idea here is that we will take those Fresnel lenses and we'll array them into a gigantic geodesic dome. So each one of these hexagons here represent about a 1/2 meter, one imaging telescope. And each telescope samples about 11 by 11 square degrees. Okay? And if you have hundreds of these telescopes, that means that we could take an image of 10,000 square degrees instantaneously. It also means we get around this problem of being only to look at one object at a time. Okay? And so our team came up with this design. We've been working really hard on this the last couple of years, and we had a lot of things to retire in our risk. So here's the idea we have, which is we want 2 of those geodesic domes to be an observatory site, okay? And they will look at, you could imagine in the left one that you have northern and southern hemisphere locations, but in the northern hemisphere, those 2 sites would look at the same plane of the sky, and they would be looking for an unambiguous detection. Okay, so we need to weed out false positives, just like Nikola Tesla. Okay? And so we'd have 2 geodesic domes that represent the PANO-SETI or panoramic SETI observatory. Where are we now? Okay, so in the last 2 years, we've made 5 of our individual Fresnel telescopes. This is one taken here. The lens is sitting at the bottom right here. This is 1/2 meters in diameter. Here's your baffling. Here's, oops, sorry about this. Here in the top is where our detector, there's a focus stage. There's a few other components missing in this when it's being assembled here. What we've really worked on, the hard work, has been designing our custom detector and electronics board. So on the bottom here represents our 32 by 32 pixels. Each one of those pixels here, right, samples the sky. So this is our 11 by 11 square degrees of a single device. Okay, and all of our hard work in collaboration with Harvard and Berkeley is the back end detector readout that has to do this processing in real time. So we have ASICs and FPGAs for those that have questions about our electronics. We've also been working on our full observatory design. So we've done custom electronics and power supply boxes that can power, tens to hundreds of these at once for an entire system. And most excitingly, in February of this year, think about the timing, folks. In February of this year, our entire team went to Lick Observatory, thanks to the Lick Observatory staff for refurbishing the astrograph dome. And we installed 2 of our first telescopes that are now collecting data on clear nights. We've been observing through COVID at Lick Observatory. So you see the Fresnel lenses here and on the back end. And the picture I have behind me, right, is this picture here. And you can see this is the astrograph dome. It opens, and here are two Fresnel telescopes pointing at the same plane of the sky. We're observing it in pajama mode. So I have students and postdocs observing and collecting data, on site every night from Lick Observatory, even through this crisis. So the timing was impeccable that we were able to get up there and commission these instruments. And while we're sitting at home this next year, we'll be collecting data and continuing our full design of the observatory. Now, I won't have time to talk about this, but PANO-SETI is incredibly interesting for other phenomena that is not SETI. So these are gamma ray bursts that occupy here. This is second time scales. Stars vary, in the minute time scales. There's supernovae, tidally disrupted events, novae that occur at variable time scales. But PANO-SETI is going to be occupying a regime that's really never been explored before. So we're very interested in coupling this into what's called multi-messenger astronomy, and in particular, LIGO and gravitational waves. I had the honor to talk to Congress in 2016 about SETI and to bring back the contact reference in this. Enthusiasm is ever increasing for SETI, both in the science community, but always in the public. But in reality, resources are scarce. I think the public thinks that this is what scientists do. We try to look for ET, but in fact, we don't. There is just a mere 24 of us really that are dedicated to this mission of SETI. So I think, what we think a lot about is how to bring in others to SETI. How do we make this scientific field thrive and move forward and try to think of new ways of searching? I just bring this up. China built the FAST telescope. Okay, it's a 500-meter telescope in the southwest of China. You can see they built it in 5 years. I'd love to put this image side by side. The Berkeley SETI Research Center is working with China to put in receivers and to begin some SETI research. I also want to mention Breakthrough Listen started in 2015. This was a program started by Yuri Milner, who is a philanthropist in the Bay Area. He was interested in sparking many different radio SETI endeavors. So he pledged $100 million over 10 years. Most of this has bought national access, both in Australia and the United States, telescope time that's dedicated for SETI. It also included an optical SETI survey at Lick using the Planet Finder, the automatic Planet Finder. I just wanted, I know I rushed through those last slides. I was just mindful of time. I wanted to also remind all of us on this call, this is the 51st year anniversary of men walking on the moon. And so, like that endeavor in SETI, I think this is a pretty, grandiose way to move forward. And I just want to take questions now if there's any been streaming through in the chat.
Sure thing. Some of the first questions were about the three-body problem and the perspective on the success of SETI. Would you be willing to talk to us a little bit about that?
I think I need to ask it, do you mean the three-body problem between stars and planets? Or maybe I should ask the person to rephrase in the chat. But
Sure.
in terms of exoplanets and the stability of exoplanets, the Kepler survey, when they did transiting exoplanets, some of those stars were quite old or older, which would imply that those solar systems were old as well. And most ejections that would occur with planets and stars would occur in the first 100 million years of their formation. And so we expect most of the solar systems that we see in older stars to be pretty stable.
Right. Can you talk to us a little bit about what the images from the panoramic SETI geodesic domes look like?
I should have put that in.
Yeah, Kelly was wondering whether it's possible to do any other science with them other than looking for bright optical or
Yeah, I'm so sorry I didn't put that in. I mean, we're getting all these data. So each pixel looks at about 1/3 of a degree. We see airplanes, we see satellites, we see bright stars drifting through. We are literally taking a picture of the night sky every nanosecond. And so we have different ways to do that. Sometimes we look for bright pulses, but we've also designed in our chips to be able to take what we call a movie mode, so we could watch things track. So there's interesting science to do with near-Earth asteroids, potentially, other fast-moving objects. And then the other question that was alluding to, I tried to get to at the end, which is things like merging neutron stars, for instance. If there was any electromagnetic or optical counterpart, we have interest of potentially seeing those. You know, the Crab pulsar does emit a unresolved down to even nanoseconds an optical pulse in its region, and this has to do with plasma physics. But to generate a photon that, you know, a pulse that is within a nanosecond, you need a really high energetic event, and it would have to compress it in a foot. And that's hard to do. So the other objects are really compact objects, which I've just kind of talked about.
Perfect. Our friend Andy Frank and Paul Warber reminded us that the Three-Body Problem is a sci-fi novel.
Oh my gosh. Okay, good. I have not read it, or if I had it, it's been years. So I apologize for not getting the reference.
No problem. Jim asked, is your infrared search able to cover all the infrared spectrum, a good part, a few parts, a very narrow band? What are the implications there?
Yeah, great question. It does not cover the entire near infrared. Usually near infrared, people even in astronomy debate it, but we usually take it about at 1 micron out to maybe 3 to 5 microns. Maybe not. Ours operates between 900 nanometers out to 1.6 microns, so about half of the near infrared range. And that has to do with being able to cool the detectors down. It's a great question.
Throughout your presentation, you talked about searching for the kind of communication and messages that folks might be sending us. Are we trying to send messages out into the universe in case somebody's looking for us?
Yeah, so my whole presentation is about listening. And the question here is, what about, you know, messaging? We have done this in the past. There's been coordinated efforts. We used the Arecibo in the 70s to send a message out to one of the globular clusters. This was coordinated with Frank Drake. There have been, for lack of a better word, there's been other rogue observatories that have sent signals. A lot of scientists, including myself, have signed, you know, letters or memos that have stated that, you know, maybe we need to listen first before we send messages. Partly because I think that if a message needs to be sent, then it should be coordinated at kind of the United Nations international level to get, you know, the diverse voices from humanity to be a part of it. But in truth, these are kind of now being done as one-offs and PR events, and I think we'll continue to have that. But there are some scientists that, like I said, we go to Congress and other people to try to talk about these issues.
A question that I've heard before during some of Natalie Botela's talks when she talks about the Drake equation is it possible that the building blocks of life here on Earth are different for life forms found elsewhere, give that they are likely to survive in conditions not conducive to the ATCG bases?
Sure, it's possible. I don't know. You know, my joy of astrobiology is really how much we don't know. And it's also how much we've learned even in the course of my short career, both about astronomy, but also genetics and other things about the initial conditions of life that many other scientists try to explore. You know, in SETI, I think that question is very interesting when we think about biosignatures and trying to look for evidence of life within another atmosphere of another planet. And in essence, SETI, when we just kind of jump over that, we kind of take this leap and say, hey, let's just look for intelligent life communicating, or we should say communicating life. And I don't care what their genetic makeup is. And maybe they're not biological at all.
You talked a little bit about archaeologists earlier. What are the odds of us not finding extraterrestrial life, but an artifact created by and left behind by extraterrestrial life? And do you have any idea of what that artifact might be?
It's a great question. I would never comment on the odds of any of this. So I always take all that with a grain of salt. But I will say that Jason Wright at Penn State has a wonderful program that he's tried to explore, looking at Kepler data with other scientists, where Kepler was looking at planets that would eclipse another star. We'd watch it dim, and that's how we knew the planet there. There were some interesting papers about saying, well, what if it wasn't a planet? What if there was some weird mega structure made by aliens that eclipsed the star? And that would leave a weird pattern. And there's been several papers, scientific papers, that talked about how you would identify that in a transit signal. And there's even people that have discussed going back and mining Kepler and other transit data set with machine learning to look for kind of oddballs.
Thank you. We have somebody in the NEOWISE is in the news a lot right now. Can you talk a little bit about that for folks who haven't heard, or folks who are still wondering if they can see that?
If you are in a clear place tonight, get outside. So Comet NEOWISE, if you're on the West Coast, will be up tonight. We have no moon at that time at sunset, which also makes it nice to look at something diffuse. It will be, if you're familiar with the Big Dipper, if you get to the end of the ladle handle at that star, you'll go down about, probably, I don't know, looking at the charts, but it's probably about 20 degrees down. And you're going to look for a fuzzy guy. By the naked eye, I went out to see it a few nights ago, but tried to go to a dark spot. It's hard to see, but with binoculars, it's fantastic. If you have a telescope, obviously a telescope is fantastic, but it's large. It's like, 5 degrees and 2 beautiful tails. So it never gets old. You guys get outside and go look at Comet NEOWISE.
Perfect. We are wrapping up on time, but I wanted to spend a few minutes to talk about our upcoming events. If you all have been part of this, you know that we go every other week with an Ask an Astronomer event. So coming up next week, we have a UCSC student who actually started our Ask an Astronomer series here, is going to be joining us. He has done a lot of Ask an Astronomer events. So he's going to have some fantastic stories about some of the great questions that he has received in the past, as well as being willing, of course, to answer your questions. You can send your questions to any of our social media links for either UCO or Lick Observatory, or of course you can continue to send those questions to our email, social@ucolick.org. In addition, the following week, our next living room lecture like this will be Dr. Ryan Foley. Some of you have heard him talk about his team's discovery. They were the first ones to see the neutron star merger just by about 5 minutes. He'll be talking to us a little bit about that and why we continue to look for neutron star collisions now that we've already seen it happen. Why do we continue to invest the billions of dollars to be able to identify more and more of these? What are the science questions? What are the implications? In the meantime, want to thank Shelley again so much for taking time away from her work and away from her family to join us in her living room. Thank you all so much for attending the University of California Observatory's living room lecture. We hope that we see you next Monday.
Thank you, everybody. Take care.